The talk tonight is on the closing the Iapetus Ocean, late and ophiolite formation in the Grampian Orogeny and implications for UK mineral potential and metal security. And our speaker tonight is Stephen Hollis, Dr. Stephen Hollis, who's a lecturer in ore systems at the University of Edinburgh, Department of Geosciences. I think that's what we call yourselves there now. It was Edinburgh Geology was when I was there. It's changed a bit since then. Stephen finished his undergraduate degree at the University of Birmingham in 2007 and completed a master's in geochemistry at the University of Leeds in 2008. His PhD at the University of Southampton focused on the evolution and mineralization of the Tyrone Igneous complex of Northern Ireland. He then undertook postdoctoral positions at the Commonwealth Scientific and Industrial Research Organisation. You planted Cyro?
Cyro, yeah.
Australia on developing new exploration techniques for volcanic massive sulfide, VMS, deposits in the greater than 2.5 billion year-old Grampian Craton in Western Australia, and at the University College Dublin, Ireland, on applications of clumped CO and PV isotopes to carbonate-hosted zinc deposits of the Irish Midlands. He's a member of the Society of Economic Geologists and has authored or co-authored some 20, I don't know why this is specifically 23 out of 30. It's somewhere in the range of 22 billion. Right, okay. Since 2011. Over to you, Stephen. Thank you very much.
Cool. Thanks everyone for the introduction and the invitation to Glasgow. It's been a while since I've been to Glasgow. Last time I was here, kind of on campus, there was an economic geology conference here. I think it was in 2016, where there was a gathering of a few thousand economic geologists. So today I'm going to talk about closing the Iapetus Ocean, which many of you will know is an ocean that used to run between the northern and southern parts of Ireland and continued through between Scotland, England, through Norway, and then through the Newfoundland and Canadian Appalachians as well. So most of this research was done during my PhD some 10, 11 years ago or so. As was just mentioned, I've been to Australia since, moved back to Ireland, and then I've been in Edinburgh about 3 years. So most of this work is PhD work, but for the last 10 years or so since, myself, Mark Cooper, have been going back to Northern Ireland to continue researching this area. And we've just had a PhD student start in September, kind of picking off where I left off about 10 years ago. So, change the slide. Okay, so the talk outline is basically twofold. The first bit is all about the closure of this Iapetus Ocean. And specifically, we're going to talk a little bit about my field area in County Tyrone and County Londonderry. And this is one of the famous archaeological sites, the Ogham Stone, and you can see the ancient carvings in it. So we're going to talk about the Tyrone Igneous complex and how it sits in the wider origin. And why this is important is the second part of the talk, which is mineral deposits and the energy transition. So as was said, I'm an economic geologist, and part of my current lecturing at Edinburgh is we talk a lot about the energy transition with students, where we're going to get our critical raw materials, where we're going to get all our zinc from, our copper, our iron, and so on. So I'm going to talk a bit about something called VMS deposits, and I'll tell you what they are and how they form. I'm going to talk about the implications for mineralization in Northern Ireland, some correlations with Newfoundland, and then I'm going to mention very briefly at the end some recce field trips we've done to Ballantrae, some future research ideas, and so on. Cool. Okay, so the closure of the Iapetus Ocean occurred during the early to mid Paleozoic, and it separated Laurentia, there's Scotland up there, there's the north of Ireland, and England and Wales and the Republic of Ireland is down here at Avalonia. So you have this large ocean that separated them during the period of, say, the kind of late Cambrian through to the early Ordovician, and this ocean started to close. And as this ocean started to close, you had subduction underneath the Laurentian system, the Laurentian continent through here, and you had a series of ophiolites and volcanic arcs develop that were then accreted to that margin. So during the kind of early closure of Iapetus, during the kind of Ordovician period, you had the arrival of lots of volcanic arcs, bits of oceanic crust, and they essentially got slapped onto that Laurentian margin. Later, during the late Caledonian period, talking about late Silurian, kind of early Devonian times, you then started to collide some of these other blocks, such as Baltica, which is Scandinavia, and Avalonia with Laurentia. So for this talk, we're really focusing on the Grampian origin through here. It's the arrival of these early arcs and ophiolites to that margin. And how is this expressed in Scotland? Well, it's responsible for all the deformation and metamorphism you see across the Scottish Highlands. So this is an image from the BGS, really complex. The point is, it's just lots and lots of folding, deformation, metamorphism caused by the arrival of outboard microcontinental blocks, ophiolites and arcs that arrived to that margin during the Ordovician period. The margin is represented by this, essentially this red dotted line. This area to the northwest, this would be Laurentia, and then through here in Scotland. And then this stuff through here, this would be called the Midland Valley terrain. And it's essentially stuff that was accreted to that Laurentian margin that caused all this deformation and metamorphism. So that arrived, it didn't all arrive at once, it arrived in several distinct phases, from the late Cambrian through to the Middle Ordovician. And our research has actually been picking apart the arrival of those outboard bits of Iapetus, so the arcs, the ophiolites, and the outriding bits of crust. Okay, so this early event of the closure of the Iapetus is called the Grampian Orogeny. And as I mentioned, this led to the metamorphism of these passive margin metasediments. So the metasediments in question are coloured in here in brown, and this is referred to as the Dalradian supergroup. I'm sure many of you are all familiar with this. The accreted material on this map of Scotland and Ireland is exposed in what's called the Midland Valley terrain. And because of lots of Silurian and Devonian and Carboniferous cover, there's actually not much of that accreted stuff preserved at the surface. You get bits of old oceanic crust along the Highland boundary fault as the Highland border ophiolite. You get some ophiolitic rocks at Ballantrae down here. You get some ophiolitic rocks and some volcanic arc rocks in Northern Ireland called the Tyrone Igneous complex, which is the biggest exposed or the most exposed sequence out of any. And then you get some remnants of volcanic arc rocks around Western Ireland, places like Charlestown, Connemara, South Mayo as well. Now, if you look at the Newfoundland system, because this whole belt continues from Scotland through Ireland into Newfoundland, they've actually done a lot of geochronology, geochemistry, and so on. And they've identified at least 3 different episodes of arcs and ophiolites arriving in that margin. What we're looking at is in Western Ireland, through here, we have an extremely well documented part of the sequence. So people like John Dewey, Paul Ryan, Amy Drought, and many others have been working on this area for about 30, 40 years, and it's extremely well documented. You have a 4-arc basin, a volcanic arc, you have blue schists, subduction channel sediments, and then the margin. So you can tell really nicely which way subduction was dipping. You can work out when the arc arrived at the margin and when the whole system started to unroof. The problem we had in Northern Ireland was there was the political turmoil of the Troubles. So this meant through the 80s and the 90s, very few people wanted to work in this area. So if we just take a look at the Western Irish system, it's relatively straightforward. This is our Laurentian margin, and we have lots of sedimentation coming off this margin. These are our Dalradian turbidites or metasedimentary rocks. Essentially, you have early subduction starts dipping away from Laurentia, and you form lots of volcanic arcs and ophiolites. These gradually get closer as the subduction system closes, and they get accreted to the margin. So this eventually clogs the subduction channel. Yep. And this arc collides with the margin. And as it collides with the margin, you start to erode some of this material from the foreland and from the arc itself into this foreland basin or this South Mayo trough through here. So in Western Ireland, you have a really classic sequence. And I'm not going to go through this at depth, but essentially you have an early ophiolite, kind of Late Cambrian age. You have a very young juvenile volcanic arc, mostly basalts, pillow-basalts, basaltic andesites. As that subduction continues and that arc approaches the margin, it gets more continental material incorporated into it, becomes more evolved, becomes more rhyolitic. As it collides, you start to get metamorphic detritus into the basin, and then subduction flips because you've clogged the channel. So we have this long protracted history from 510 million years all the way to about 454 million years. This is a classic example globally of how arc systems develop. They collide with margins, you get orogenic unroofing, and you see changes in the nature of the sediments recorded in the basins. From early ophiolitic material, lots of chrome spinel, through to then, say, clasts of granite, lava, and then lots and lots of metamorphic detritus. Which brings us to Northern Ireland. As I mentioned, this is actually one of the largest areas of exposed arcs and ophiolites in the entire Caledonides through this sector. Very little work was done because of the Troubles. Very little work was done because of the nature of the exposure. There's a lot of sand and gravel through this area. Very little outcrop. It makes it very hard to do research. So there were a few papers. Donny Hutton, many of you might know Donny Hutton. He was working in this area in the kind of late 80s, early 90s, produced a number of key papers. He had a Nature paper where he discovered there was in fact an ophiolite in this region and did some preliminary work on the volcanic arc. But it wasn't until kind of the 2000s where we started to do a lot more research. One of the main things that was done was there was a geophysical and geochemical survey done across Ireland. And this was called the TELUS project. So it was flown by the Northern Irish government. This is a magnetics map of Northern Ireland. They flew magnetics, electromagnetics, radiometrics. They also did systematic soil sampling, stream water sampling, and stream sediment sampling. And one of the main goals, in addition to better map out the underlying unexposed geology, was to look for mineral deposits. And here you can see a gold in soils map of the north of Ireland. This was actually really successful. There was lots of exploration interest in Northern Ireland because of the TELUS project, and TELUS is now systematically covering the rest of the island of Ireland. So my PhD started just after TELUS was flown, started in 2008, went to about 2012. And this is the magnetics map shown with the existing line work. And you can see the amount of detail that the magnetics are showing us. So my project was lots and lots of field work, about 6 months of mapping, lots of geochemistry, lots of geochronology, and lots of isotope research. This was the existing framework or the line work for what the complex looks like. And there's a lot of different units here. I'm going to break it down into 4 main bits, or 5 main bits. To the northwest of this thing called the Oma Frost, this is essentially the Laurentian margin. This is our Dalradian supergroup through here. So it's Samites, semi-peelites, peelites. Typical Dalradian you get across the Scottish Highlands. This bit in brown through the middle, this is also Dalradian metasedimentary rocks. These have just experienced much higher grades of metamorphism. So we call it the metamorphic basement. Whereas this is kind of green schist to amphibolite. This is up to sillimanite grade. So this is what we've accreted our ophiolite onto, and we've pushed our arc on top of. See much higher temperatures and pressures. All this stuff through here, this is our volcanic arc. It's known as the Tyrone volcanic group. And the stuff in purple through here, this is called the Tyrone plutonic group, and that's essentially our ophiolite. So we have an arc, an ophiolite, and some metamorphic basement. We also have lots and lots of granites or granitoids, intrusions of tonalite, granite, quartz porphyry, diorite, monzogranite, and so on, that intrude all parts of the arc, the ophiolite, and the basement. And these essentially stitch everything together. So you have an outboard bit of Laurentia in brown. You've plopped your ophiolite on the top. You've built your arc on top of that. And then you've intruded lots and lots of granitoids. There's another one down here, which is S-type granite. And we'll come back to that. That's quite rare in the area. And we'll come back to that in a few slides' time. Okay, so let's start with the metamorphic basement. What does it look like? You get typical gneissos, rocks, some schists, and it's essentially metamorphosed Dalradian turbidites. So if you took the Scottish Highlands and you subjected them to a bit more temperature and pressure, they'd essentially look like this. So the detrital zircon signatures match the Dalradian supergroup. It's just the temperatures and pressures are a little bit higher. And Dave Chew from Trinity College Dublin has done a lot of geochronology and has determined that this deformation and metamorphism occurred during this period known as the Grampian Orogeny, where this ophiolite and R collided. This is some recent field photos. So this is, well, not so recent, maybe 5 years ago. These are some more gneissos rocks, and you can see the fabrics are cross-cut by some late pegmatites that are kind of, you have partial melting, and they're kind of eating their way up through the stratigraphy. You have some earlier leucosomes and kind of mineral segregations. If we go to the next part of the sequence, we'll talk about our Tyrone plutonic group. This is our ophiolite, remember in purple, through here. So if we look at Tellus, our ophiolite is exposed through this region. This is an EM map. You can't really get much distinction from that. If you look at the magnetics map, you can start to identify different slices of ophiolitic material through here. The ophiolite, as it arrived, it didn't arrive onto the outboard block as one sheet. It arrived and was preserved as several tectonic slices of oceanic crust. Some of these have been dated 484 and 480 million years old. So this is kind of the traumatic or earliest Ordovician when this bit of oceanic crust formed. There are other bits of the ophiolite which haven't been dated, and that is ongoing research. If we look at the geochemistry of this ophiolite, it's like every other ophiolite in the Caledonides and in the Appalachians. It essentially formed above a subduction zone. So 480 million years ago, we had a subduction system off the coast of Laurentia forming the Tyrone plutonic group. The geochemistry is the same as subduction affinity ophiolites all over the world. And these are some of the typical rocks we get. We get lots and lots of gabbros, isotropic gabbros, layered gabbros, pegmatitic gabbros, intruded by sheeted dikes. And then we get little bits of the top of the ophiolite sequence, so very rare pillow lavas. So we've essentially preserved most of the upper to middle part of some oceanic crust formed in Iapetus. Yep. Here are a couple more field photos. So this is a pegmatitic gabbro from a place called Black Rock. And here you can see the size of some of these amphibole crystals, giving you a kind of scale for kind of the water content and the variety of the rocks exposed in Tyrone. It's also intruded by some later quartz feldspar pegmatitic sheets. We don't know the age of these. They cross-cut some of the fabrics in the ophiolite, and this is a future target for dating. Near the base of the ophiolite, we see lots and lots of melting towards the contact with those underlying Dalradian metasedimentary rocks. So this is an area called Blaeberry Rock. You get lots of blaeberries there, and it's exposed in the Dava forest. There was a tiny bit of rock exposed. We peeled off the bog and found these amazing geological relationships. This is lots and lots of melting of those Dalradian metasediments. It's being deformed and injected into a still hot ophiolite towards its base. So we see lots of syn-deformational melting and then cross-cutting kind of apolitic to granitic sheets as well. Lots of rotated amphibole, porphyroblasts, and so on. Recent field work we did a couple of years ago. We went to a sand and gravel pit, and we found lots more melting around the base of the ophiolite, as you'd expect. You get this hot ophiolite coming over the top of relatively cold metasedimentary rocks. Some of these melts we've actually sampled, and we're going to put in a bid with NERC to try and do some more geochronology to try and establish the time of this melting and therefore potentially the timing of ophiolite abduction. One thing we have found is, I mentioned a few slides ago, there was a rare occurrence of S-type granite. All other occurrences of granite in the Tyrone complex are I-types. They're formed from the melting of igneous material. This one, however, exposed at Tremoge Glen, is muscovite bearing and has typical geochemical affinities of S-type granites. We've done the geochronology on this, and the age of it is just after the age of the ophiolite. So we think you have your outboard Dalradian metasediments, you form your ophiolite in the traumatic, it then comes over the top, forms all that melting, and that melt pockets and accumulates and forms these S-type granites that we see around Tremoge Glen and the margins of the ophiolite. So that happens at 478. Then we have a bit of a gap, and we don't see our next rocks until around 473. So there's a gap of about 5 million years, which is when we start to form our Tyrone volcanic group, or our arc. So we remapped the arc using all that TELUS geophysics into lots of different formations. The details aren't particularly important, but there's a variety of lithologies. So you get some nice pillow basalts through here. You get some iron formations, layered cherts, rhyolite breccias, and so on. It's a really variable sequence. And in a minute, I'm going to talk about why this variation is important in terms of mineralization. But effectively, we've established there are at least 5 distinct formations through geochemistry and the geochronology. Yep. This arc is extremely short-lived. This arc, despite being one of the most extensive areas in the Caledonides, only existed for about 4 or 5 million years. Compare that to the Loch Nafui arc. That was around for about 10, 15 million years and shows a progressive evolution. So we've dated a lot of different rocks from the stratigraphy. Here's all these different formations. And we keep getting the same ages. The oldest bit is about 473 million years, and the youngest part is around 469 MA. So we've dated a variety of different rhyolites, tuffs, and intrusions, cutting all of these different formations. So our arc is younger than our ophiolite and considerably younger than the arc in Western Ireland. And we have extensive geochemistry, which has revealed a very complex history. Yep. So if you look at this arc sequence, I'll just point out a few things. The lower portion down here in green and purple, this is mostly basalt to basaltic andesite to andesite dominated. The upper bit in yellow is mostly rhyolite dominated. But at all stratigraphic levels, you get these purple units through here, and these are rift lavas. So these are typical of modern arc systems where you have extreme amounts of extension, and you produce lavas which actually lack an arc geochemical signature. They lack the classic niobium anomalies, zirconium anomalies, and so on. At the same time, you get these rift basalts. You also get lots and lots of exhalites, so jaspers, iron formations. You get lots of hydrothermal alteration, and you get lots of sniffs of gold, copper, zinc, and lead mineralization. So these episodes of rifting in this short-lived arc system, as you're pulling it apart due to extension, this is where we should be looking for our mineral deposit. We don't see any of this evidence for intra-arc rifting in Western Ireland. The only places we see it is Northern Ireland and Ballantrae. So this is important for where to look for mineral deposits. Okay, so after all that formed, you have your Laurentian margin, you have your outboard bit of metasediments. You've accreted your ophiolite onto those metasediments while the ophiolite's still hot, and then you formed your arc over the top. Afterwards, you intruded lots and lots of granites, tonalites, quartz porphyries, and so on. We've done about 12 age dates for these things, and they essentially stitch all of this together. It's a continuation of the arc system, it's calc-alkaline, and so on. But importantly, they contain inherited zircons from this metamorphic basement, so they've come through the entire thing. Yep. So putting it all together, this is our Tyrone story. So we have an early ophiolite forms in the traumatic. It then gets abducted onto that outboard bit of margin, starts to melt it, produces that S-type granite at 478. 473, we start to see our arc form, and then it's all over by 464. But throughout that entire period, we've had lots and lots of rifting, intra-arc extension, and lots of rift basalts and hydrothermal alteration through that part of the stratigraphy. Yep. If we compare this to Western Ireland, remember we have our ophiolite down here at 510. It's way off the diagram down here somewhere. We have a juvenile arc from 500 going through to 480 until we start to see any rhyolites. Then we collide the system, and then we have the unroofing. Our ophiolite is much younger in Tyrone. Our arc is also much younger and much shorter lived. And in Tyrone, we have this disorganized rifting, which is important for mineralization. Which brings me on to the second part of the talk. So there's a saying that we love to say to the first years, if you can't mine it, you have to grow it. No, the other way around. If you can't grow it, you have to mine it. So the Earth's crust is basically where we get all of our stuff as a society. We get all the iron to build this, lecture theatre. We get the copper for the wiring. We dig out all the sand and gravel, all the roadstone, and everything comes from mines and quarries such as this. This is Bingen Canyon in the US. It's a major copper deposit. So the Earth's crust is basically where we get all of our stuff as a society. We get all the iron to build this, lecture theatre. We dig out all the sand and gravel, all the roadstone, and everything comes from mines and quarries such as this. This is Bingen Canyon in the US. It's a major copper deposit. So geology or mining and quarrying is the first port of call for all of society's needs, essentially. And we're aware as a society this is an environmentally damaging process, and there's lots of talk now about CO2, the energy transition, and trying to get to a cleaner society. If you think about what your average person will need over their lifetime, these numbers are a little bit old, but they haven't really changed. Each one of us needs a lot of material just to survive. We need lots of zinc, lots of lead, copper for all the electrical wiring you're ever going to use in your lifetime, lots of stone, sand and gravel for concrete, roads, so on, phosphate rock for fertilizer, iron ore, and so on. All this has to come out the ground, and we need it as a society. If you look at this global map of the world, you can see the areas where most of the human development currently is. These raw materials are required for infrastructure, heat, energy, light, communication, transportation, and so on. So we need all of these materials to survive as a society. If you look at global projections for population, this is where we are at the moment, around 8 billion people. By the end of the century, it's predicted we're going to be over 10 billion people, which is largely due to an explosion in the population in Africa, which is going to require lots and lots of industrial development. So these parts of the globe are going to require huge amounts of resources, iron ore, copper, aluminium, zinc, lead, and so on. If you look at Shanghai, this is the 26-year-old transformation of Shanghai from 1987 to 2013. And this required, again, just to labour the point, large amounts of raw materials. So following on from the earlier quote, which I mucked up, here's a second one, which is, if you haven't mined it, you can't recycle it. So this is the importance of the green energy transition. Globally, with an increasing population, we're going to need lots of iron, lots of copper, lots of zinc, and so on. But in terms of stuff that goes into electric vehicles, tellurium, gold, silver, cobalt, the rare earths, lithium, and so on, we haven't traditionally mined a lot of these metals. So we don't have sufficient stockpiles to recycle them. So while we don't need that much of it for the energy transition, we still need lots of mining going forward, not only to mine the stuff for our green technologies, but for that future population increase. And it's been predicted by a recent report that we're going to need 6.5 billion tons of metal for the green energy transition. Mostly iron to build stuff like steel, copper for electric wiring, aluminium, and so on. We're going to have a massive expansion of the electricity grid if we go through this from 75 million kilometers globally to 200 million kilometers. And we're going to need over 250 new mines for this to happen. Which brings me on back to County Tyrone. So there's a type of mineral deposit that forms on the seafloor, and you may have seen these kind of black smoker systems in the past. These things vent out very hot fluids up to 250, 350 degrees that carry lots and lots of metal in solution. And they form chimneys on the seafloor that then collapse and they form mounds and so on. And we don't currently mine them on the seafloor, but what we do is we mine them in the ancient rock record. So these things form in submarine environments, in bits of oceanic crust, in volcanic arcs, in volcanic back arcs, and so on. And they're termed VMS deposits. So volcanogenic, because they're volcanic hosted, massive sulfide deposits. So there are a few things that you need for these things to form that I'll show you on the next slide. But crucially, if you go back, it's all right, don't worry. The few things they can contain is they contain lots of copper for your wiring, lots of zinc to galvanize your steel. They can contain lead and significantly lots and lots of these new metals that we need for the energy transition. contain cobalt, they contain bismuth, indium, germanium, antimony, tellurium, and so on. Not as the main product that's mined, but as a byproduct of that copper, zinc mining. Yep. Thanks. Okay, so the VMS ingredients list is essentially to form one of these deposits, you need a submarine setting, which we have in County Tyrone. It's a submarine volcanic arc with lots of pillow lavas, cherts, black shales, and so on. You need extensive volcanic and magmatic activity. This is to basically get a hydrothermal convection cell where you take cold seawater, heat it up, strip the metals from depth, and then you take these metal-bearing fluids back towards the seafloor where they form your ore bodies. So you need a submarine setting, lots of volcanism, lots of subvolcanic intrusions, rifting or extension to get the fluids down and back up through fault systems, and potentially a magmatic source for some of the metals. So County Tyrone is looking very encouraging just from our VMS ingredients list. And depending on which rocks you leach the metal from, you can get different metals in your deposits, but we'll leave that for another time. So what makes us so confident we get these types of deposits in our arc and our ophiolite in Northern Ireland? Well, if you go over to the continuation of the Grampian in Newfoundland, you get lots and lots of these mineral deposits, and they've been mined for over 100 years. So they've got 68 deposits, and they've got some of the most metal-rich VMS deposits in the world at Buckens, in here. And they've got some of the largest tonnage VMS deposits in the world down here at New Brunswick. This deposit is 230 million tons of mineralization in one main lens or a few main lenses. So our geology continues into their geology. Their geology, they have lots of mineral deposits. So do we have any mineral deposits in our area? So as I mentioned earlier, these are some of the most metal-rich deposits and can be some of the largest tonnage ones. Significantly, if you look at the Newfoundland Grampian system, and I'm not going to go into this, they essentially have 3 different episodes of arcs and ophiolites arriving to that margin and colliding with it. And significantly, all the good stuff occurs in the 3rd phase, called the Aniopscotch accretionary tract, which hosts the Buckens deposits. If you look at the age, it's looking quite similar to County Tyrone. Yep. So we did a broad comparison between their area and our area. Here's their area on the right. Here's our area through the middle. If you look at the nature of what the stuff was accreted to, it's very, very similar. They have an ophiolite, we have an ophiolite. Theirs is essentially the same age as our ophiolite. The timing of accretion is basically the same. They have an island arc, we have an island arc. The ages are essentially the same. The geochemistry of their arc is essentially the same as ours. They have lots of disorganized rifting, lots of these basalts throughout the stratigraphy. They have same affinity of the rhyolites. The granites arrive at the same time. The tonalites arrive at the same time. And the only real difference between these two areas is they have lots and lots of mineralization, and we haven't really found it yet. Thanks. So, are there VMS deposits in Tyrone? This is a map of the Buckens-Roberts Arm Belt, and they've essentially divided it into 4 different formations. The names don't really matter, but we have equivalent formations in the Tyrone Igneous complex to their formations. Similar geology, similar tectonic setting, similar geochemical affinity, and so on. So the ones with all their VMS deposits are in something called the Buckens River Formation, which is kind of a lot like something we term the Greencastle Formation. So what we did in 2011, towards the end of my PhD, went to work with a mining company for a year, and we got some Canadians over. Canadians are really good at finding mineralization, it seems. Got a very famous prospecting family called the Keats family. Found a lot of those deposits in Newfoundland going back several generations. And they found lots and lots of new mineral occurrences all throughout Tyrone Igneous complex, specifically the volcanic group in the Greencastle Formation. So some of these are pretty decent outcrops for mineralization. Most of these still haven't been drilled to see if they thicken up or continue at depth, but certainly we have lots and lots of gold knocking around, lots of base metal mineralization and so on, through here in this Greencastle Formation in the blue bit. We also have widespread hydrothermal alteration all the way across the Greencastle Formation and soil anomalies which continue on for kilometres. So this is all looking pretty prospective. If you were to hide the Buckens deposits in the Greencastle Formation, there'd be these little black blobs in here. You can see there's lots of places to hide them, considering we have about 5% outcrop exposure, and these could be at 200 meters depth, 300 meters depth, and so on. Here we go. Okay, so after this was done, as I mentioned, we've been going back year after year, doing more field work, trying to refine the regional tectonic model of the Tyrone Igneous complex from an academic point of view, but also Dalradian and Gold are interested in mineral exploration in this region. So this was a student field trip we went on, and there's a rally track up there where a farmer has carved into a rhyolite a nice little rally track for that you can drive around his Fiesta on and charge the local people. And unfortunately for him, he's on silicified rhyolite, so it's probably wreaking havoc on the tyres of the cars. But there's lots and lots of copper all the way around this rally track associated with one of these rhyolite domes. So this is all chalcopyrite through here, and pyrite. This is malachite. This is secondary copper mineralization. This is just a lump that we managed to whack off one of the walls. And again, we're seeing lots and lots of mineralization also in the metamorphic basement. Walkabout Resources have the adjacent license, and we're looking within the metamorphic basement. They found sniffs of cobalt mineralization, bismuth and silver mineralization, again in volcanic rocks, and lots of copper gold mineralization associated with late intrusions. This was back in 2018. Okay, so Tyrone is looking very, very prospective for mineralization. It's gone a little bit quiet in recent years. There's a lot more focus there on the gold in the adjacent Dalradian supergroup. They have a world-class gold deposit called Coreignault. So because we're kind of finishing up working on Tyrone, we've started to look a little bit more at Ballantrae. So Ballantrae, many of you probably know, is exposed in Western Scotland, and it has a lot of similarities with the Tyrone Igneous complex. You have these sheets of ophiolitic material, mostly serpentinites, but bits of gabbros and sheeted dikes as well. You have lots of volcanic arc rocks through here in the green. The ophiolite is a very similar age to our ophiolite. The arcs, volcanics, are a similar age, around 475. And the accretion of the ophiolite, again, was a similar timing. It was around 478. Significantly, they see lots and lots of these rift basalts at Ballantrae. They call them within plate basalts. They're essentially what happens when you take an arc and you extend it. You can get lots of upwelling asthenosphere, which lacks an arc signature, that erupts out through propagating rifts. So we started to think Ballantrae is looking pretty good for mineralization, and specific types of VMS mineralization, particularly copper-rich and copper-zinc-rich deposits. Yep. So we first went to Ballantrae in 2014, where we were just looking at the local geology with Phil Stone. There's Phil, and that's Richard Harrington from the Natural History Museum. And we kind of walked along the beach section. We were almost done. We decided to have our lunch, and we sat down and then realized we were sitting on semi-massive sulfide, mostly pyrite, but lots and lots of malachite on the beach. So this kind of piqued our interest that there should be mineralization here. I had a master's student last year, Patrick Brown. We went and remapped Pinbane Beach. kind of down this region. And again, we're finding lots and lots of sniffs of copper mineralization associated with these within plate basalts. I must point out this is not economic copper mineralization, but it's certainly encouraging that there is some mineralization there. Okay, so we've focused a lot about all the stuff on the northern half of Iapetus. So all through the Grampian, from Tyrone, Ballantrae into Newfoundland. Well, there's a whole other side of Iapetus that is also prospective for this type of mineralization. This is Paris Mountain. This is a photo I took as an undergrad in 2008. And this is stringer mineralization for a VMS deposit that was first mined, I think, during the Bronze Age, then by the Romans, then during the time of the Battle of Trafalgar, and then now it's being more recently explored to this present day. But there's mined VMS deposits at Paris Mountain on the southern half of Iapetus in similar arc sequences, and they have a similar deposit at Avoca south of Dublin in equivalent arc volcanics as well. These were actually used to make these old late 18th century condo tokens, basically that you would find in your change if you're around back then. So this one is from Avoca, and this is from a druid from Paris Mountain. So it's worth having a revisit of these arc and ophiolite sequences, because modern techniques now, geochemical techniques, geophysical techniques, it's now possible to try and find mineralization that might have been missed 40 years ago. And this brings us to the TELUS project, which started this research back in 2008, 2006. The TELUS was originally flown over Northern Ireland. This is the continuation of the TELUS magnetics data set. There's Connemara, Galway, there's North Mayo, there's Dublin. So you can see they're slowly flying the rest of the country through geophysics. So there's a perfect opportunity now to completely remap the Avoca volcanics, which host the VMS deposits, use modern geochemistry, geochronology to identify more prospective time horizons and new mineralization. And it's important to note, without TELUS, we couldn't have done what we did in Tyrone because the exposure is absolutely terrible. So if Scotland wants to increase its mineral exploration activity, this is something that could be done over selected areas of Scotland, flying geophysical surveys to help the remapping of some of the key poorly exposed regions. Yep. Which brings us to finally the last slide, to UK supply. There's been a big push, you've probably seen it in the media, for the UK to become more self-reliant on its metals. This is a map put out by the British Geological Survey late last year, where they were flagging different areas of the UK's geology that are prospective for critical raw materials. So stuff like cobalt, lithium, tellurium, tin, indium, and so on. Here's Cornwall, where they're getting the potential lithium deposits down here, and they're trying to open up a mine. Here's some of the mineralization in Pembrokeshire. Here's Paris Mountain in northwest Wales. There's County Tyrone, and there's Ballantrae, which didn't get a mention. But there's other areas in the UK that are equally as prospective for other types of mineral deposits, because moving forward, we're seeing lots and lots of restrictions globally. Places like China saying you can't have our deposits of rare earth deposits if you do X. And they can use these raw materials as a geopolitical bargaining chip, essentially. So the UK is trying to become more self-reliant. There are deposits of tellurium associated with the gold in Northern Ireland, but as I've also shown you, there's potential copper, zinc, lead, maybe some cobalt, bismuth, and so on that might be discovered there as well. So, cool. I think that's the end of the talk. So if any of you have any questions, yeah, thank you very much.